traditional 5-minute delay, so we'll get started. It's always the key to bring in the last few people. Before, something I keep forgetting, which I'm going to put on the first slide so you actually see it now. These lectures so far have been taped for us, and they are on the synagogue website at synagogue.org, which is an easy name to remember for a synagogue website. Right in that middle column, you go down where it announces lectures, and there are links right there. They're on YouTube. So if you miss something or you want to hear something again, that's available for us to go back and use, and for my kids to watch as they get older, which will be fun also. Also, if you have questions or anything else you want to reach me for any reason, my email address is president@synagogue.org. Should also be easy to remember. So anytime, any questions, whether it's physics or something else, but you can use that for the physics as well. So synagogue.org, we get my number of page count. Something. Okay. Today, nucleons and particles. What we have been talking about until now has been stuff that interacts with the real world that we kind of touch and feel and see. The atomic physics stuff was a lot of things about how light works and how, what happens when you actually touch things and all those processes that are really part of our daily lives. Everything we experience every day is almost entirely atomic physics, the subject of the first 1.5 lectures. Nuclear physics affects us from a technology perspective, from a lot of the nuclear power plants, atomic bombs, all these kinds of things, the things you kind of need to know about in the world. So it's still something that has direct application to technology or other things we interact with. What we're getting into today is a little bit different. Now it starts to get a little weird, if it wasn't weird enough before with some of these other things. What we're talking about now is particle physics. Particle physics is the stuff the universe is really made out of, the really tiny stuff, because atoms are huge compared to anything we're doing. Even nuclei are very large compared to what we're talking about today. We're talking about the fundamental particles. They behave with their own strange set of rules, some of which are literally strange, we'll see. And a lot of concepts that are not necessarily intuitive. This stuff is on that chart that I had at the beginning of the practical to the sexy, where the practical is chemistry, and the sexy gets down toward particle physics and string theory. We're on the sexy side here. The stuff I'm talking about today won't necessarily help you understand stuff in your daily life, but it will help you understand why physics is important to people, why people get excited about it, and why we spend billions of dollars on giant machines to try to study these things. What's really attractive to people. There's two reasons for that. One is there's a bias in physics overall toward the more fundamental, toward explaining what the universe really is. And it's very tantalizing because it really feels at this stage like we're getting down to what the universe really is made out of. Not just approximations or things that are sort of nearby. But now we get that first taste of we really understand what's going on. The second reason this is appealing to everyone who's into this sort of thing is the period of history that we're in. A lot of this stuff was being developed and is still being developed now. It's a very active period. Everything I'm talking about today was within most of our lifetimes. When most of us were born in this room, most of this stuff was unknown. I'll talk a little bit about that today as well. I'll talk a little more about the history today than I have before, not in too much detail, but just enough to give you a sense of what makes this stuff exciting to a lot of people. So ultimately what I wanted to do is be able to talk about nucleon physics. What is inside a proton? We got to the nucleus, we talked about neutrons and protons. I kind of teased us with what is inside these things, these quarks or something like that. And we want to really get to that. We want to understand still what real matter is made out of, what the universe is fundamentally made out of. But we can't quite get there directly. To get there, we have to understand what particle physics really is, what these constituent parts are and the rules they behave with. The actual nucleon physics, what is inside a proton, was not accurately understood until fairly recently, maybe 20 years ago. So all of this stuff had to be figured out first before we get to that. So we're going to take a jump down to the smaller size stuff, the particle physics stuff, and along the way we'll step back and look at what a good example of that, which is what the standard matter stuff is. Most of this is going to be talking about the standard model. Now there's standard models of all kinds of things. If you say the standard model, if you Google the standard model, you will get the standard model of particle physics, because that is the standard model. Everything else is the standard solar model or the standard model, whatever it is. But this is really it's such in a sense, a miracle that everything worked out right. Its predictive power has been really astounding. There are a lot of elements of it that no one believed when they came up with it. There's a lot of stuff that people said, well, let's just stick this in here as a placeholder. And in the end, all this was experimentally confirmed. There's nothing in the standard model that looks wrong. That does not mean it's complete. There's certainly things that it doesn't explain. And there's also the possibility that it could be extended. There could be other parts to it that we haven't found yet. But the standard model itself is remarkably solid in what it's been able to do, which is part of what drives the excitement here. So a lot of that is just what the elementary particles are and what the fundamental forces between those particles are. Now I'm going to have to bounce back and forth a little bit because this kind of stuff you have to, in a way, you have to understand it before you can understand it. So I'll lay out what the particles are, and then I'll talk about what the forces are between them. And that will help us understand why the particles are laid out that way and what the differences between them are. At first, it's really just going to be the names of these things. And you won't understand why they're grouped the way they are. Then the forces will drive what that grouping is. So we'll go back and forth between those two things. Once we have that, we have the pieces. Now we can start building stuff. We can make the universe out of these things. Now we have all the basic Legos. We can start putting them together. And that's where we get to the zoo of particles. And this is where we get into history. Because now, if I start with these things, then I can figure out what I can make, and it all makes sense. Historically, first they came up with this zoo of particles, these hundreds and hundreds of particles that people kept discovering, and had no idea how to make sense of this complete mess, and had to work backward to figure out what the standard model was. So we can cheat a little bit there and do it in order. Then once we have that model built, we can look at how to use it a little bit and talk about matter versus antimatter, what happens when they come together. You hear about those, they annihilate, there's an explosion, that kind of thing. We'll understand what that really is. And that's one place where the sci-fi aspect is relatively close to being accurate. And then Feynman diagrams, which are something we'll get to with some of the pictures I sort of drew a little bit of, and we'll see what those are, because that really is what helps us do particle physics on a practical basis. And then there's a couple things we'll get to. The spin crisis and the solar neutrino deficit are specific examples of questions that were only answered in very recent years using some of this, using some new information, and what I'll call extensions to the standard model. One thing, when you see extensions to the standard model, once you have the basic standard model, once you discover something new, that's outside the standard model. But if it's true, then it becomes part of the standard model. So depending on when you're reading an article from, something will be considered part of the standard model or outside the standard model. And once it's accepted, it kind of goes in. So it eats everything. Okay, so the guys we're talking about, previous weeks, we had 2 or 3 pictures up here. All of a sudden now, I've got a whole bunch of pictures of the different Jewish Nobel Prize winning physicists here that did a lot of this work. That's because it's partly historical accident, that the sexy stuff is what's going to get the prizes. The stuff that's being actively done in this time period, I mean, the prize was only started, it's really just a 20th century thing until the 21st century. And so a lot of this activity has happened more recently, and the dates for these things are mostly fairly recent. One thing I want to point out also is there's a community of people that are doing this work. This is not one guy's thing that he went off and discovered everything. It's really kind of the interplay between each and every one of these guys. Yeah.
You said that physicists generally do most of their work when they're young. These look like a lot of old guys.
They do. They do look like old guys. A lot of that is because of just when the pictures are taken. When you're young, you don't take a lot of pictures of yourself doing your work. When you win the prize, and when the prize is eventually awarded to you, and for the most part, there's a delay.
So it's old news.
It's old news. It's old news. If you go to I always play back and forth with which pictures to use. Sometimes what's best is to use the pictures that are most familiar to people, or if they say, oh yeah, that's a picture of that guy. Some of them just look a little older than they are. But one of these guys talked about a little bit last time the connections between things. I brought a few artifacts here. This was a poster from a lecture when I was at Berkeley. It was the Segre Distinguished Lectureship. So this is Segre. The lecture was named after him, and the guy giving the lecture was Hans Bethe, who we talked about in nuclear physics in the past. The guy who's responsible for the nucleogenesis, stellar nucleogenesis, how the different elements are able to be created inside stars, as well as most of other nuclear physics. So it's Bethe who got the prize a while ago with Segre. as his sponsor. Segre is of interest to me because he is my academic great-great-grandfather. In academia, your advisor is your parent, your advisor's advisor is your grandparent, and so on. So my advisor's parent was C.S. Wu, who is usually the example held up as the clearest bias of the Nobel Prize Committee against women. She's a Chinese woman, and the work that she did, the Nobel Prize was given for it, but it wasn't given to her. It was given to the theorists that also worked at the same time. Typically, a prize would have been given to Wolfram Touchette. So that was Wu. Wu's advisor was Emilio Segre, and Segre's advisor was Enrico Fermi, who's one of the people here. So that's my lineage going back. It's easier to go back than it is to go. So that's who we have. There's a lot of these guys. These are just words we'll talk about, and we can come back to this. But the antiproton, really antimatter, is Segre. Charm, the charm quark we'll talk about in a minute. Strangeness, the strange quark. And Gelman was really responsible for coming up with the structure that we'll show in a second. The tau is one of those first extensions to the standard model where we added another generation of particles. Neutrinos, and the detection of neutrinos is important this week and more important next week. Feynman is probably the most popular of any of these guys altogether.
Are these theoretical physicists or experimental?
They're mostly theoretical physicists. As you get further on, the experimentalists start to get awarded the prize a little more recently. But most of these guys are theorists. The muon neutrino, which meant we had a different kind of neutrino here, and then the psi, which is a fun story. That one we'll get to when we talk about the history a little bit. Okay, I'm going to put this up here, and this is kind of a map to look back to as I show what the particles actually are. This is really the categorization of things. I realized as I was thinking about what to talk about that if you aren't living in this, all these things sound the same. We have fermions, leptons, bosons, hadrons, baryons, mesons. What is the difference between all this? So I drew a little map for us to kind of keep track of what's going on. This represents what all the possible elementary particles are. And the basic categories are leptons and quarks. Those are the things that make up stuff. And then over here we have the force carriers, which transmit the forces between different kinds of particles back and forth. The way these are categorized side by side, one of them is bosons and one is fermions. That really just refers to the spin of the particle. If the spin is half integer, then it's a fermion. And if it's an integer, 0, 1, 2, 3, then it's a boson. Most of these things, the elementary particles, are going to be spin 1/2, or spin 0, or spin 1. But if I start making piles of them, then I can get to these other fractional spins, 3/2, 5/2, 2, 3, 4. The spins control how these things behave in the sense that we talked briefly in the first week about the Pauli exclusion principle, which says that essentially we think no two things can occupy the same space at the same time. That's the kind of lay version of this. If I have two identical particles, they can't be in the same spot doing the same thing if they're fermions, if they have half integer spin. If they're bosons and they have integer spin, then they can. I can pile them up all in the same place. And that's the fundamental difference between these things. The consequence is the energy levels that I have in atoms. The reason I need those levels as I put more electrons in is because the lower levels fill up. And I can't keep putting more electrons in the same places. They're full because electrons have this half integer spin. I can't keep piling them to the same place. Lasers depend on having all of the light, all the photons go together in lockstep, all piled up. Lasers are possible because photons are bosons, because they have integer spin, so I can pile them all up and keep them all together. And so that's the fundamental distinction between these two kinds of things. Now, I'm going to start mapping this thing out. I have on the one side here leptons. I have the electron, I have the muon, and I have the tau. In many of these cases, we use Greek letters, and sometimes we use English letters back and forth. Essentially what happens is you run out of an alphabet, and then you have to use letters from a different alphabet. And there's one we'll get to that's kind of a Chinese letter that just looks like English. And then I have neutrinos. And it turns out that I need 3 different neutrinos. And one of them is the electron neutrino, the muon neutrino, and the tau neutrino. So these are my leptons over here. These are 3 different generations of these leptons. And then I have the quarks. I grow a little bit too big. So I'm going to shrink the tau a little bit. Here's my tau neutrino. And now I'm going to have my quarks. I have up, down, charm, strange, and these days top and bottom. Originally that was truth and beauty, but for the reasons we'll see, we decided top and bottom was a little easier. More appropriate. This is what I have. Now, yep.
Where's the neutrino here? Neutrino, right?
These are the neutrinos.
No, but what is neutrino?
What is neutrino? Right now, it's...
What I'm really asking is, what is the neutrino here? Not electron neutrino, but neutrino.
Right. Neutrino is something it turns out you need. At this point, before we get to what the interactions are, that's all there is to know about it. It's a particle that does not feel any charge.
Oh, I see. It doesn't belong here. Is that correct?
It belongs here, but when we get to the forces, what makes these things different from each other is which forces they feel. And so we'll see which forces those feel.
All this is inside the neutron.
Not necessarily. These are the basic building blocks of everything.
Okay.
So everything that has ever been created in the universe or whatever, it's all made out of these things. So these are the basic parts. These are the fermions. These are the things that stuff is made out of. And then I have the force carriers, which are the parts over here, the bosons. And those are, one of which is familiar, the photon.
Or an ion.
Or an ion, yes.
Right, it's an
Gamma.
ion.
And I have, there is an alpha, aleph somewhere in this mix. There's the W, the Z, there's actually 2 W's. There's W plus and W minus, we just call them W's. The Z is Z0. And then I have the gluons, which are just G. There's actually 8 of them, but we'll worry about that later. No one ever distinguishes between the different kinds of gluons. That's generally not important. You can't see them individually, so it doesn't matter. But for you've got 1 photon, 2 W's, Z, and a gluon. And these things mediate the forces back and forth. That's how the forces are exchanged between the different particles, and they behave differently. They're different sizes. The photon has no mass, moves at the speed of light. This is light. W's and Z's are fairly heavy. And then the gluon is its own kind of thing. Yep.
I don't know if you covered this, but the fermions and the bosons,
Right.
not the bosons, the fermions, are they in atoms? Like where are they?
Some of them are. Your basic atom
Right,
will have, it's got electrons on the outside.
right.
And that's the electron here. It has the neutrons and protons, which are mostly made up of up and down quarks.
Okay.
So these are the quarks, and these are the leptons. Now, the properties of these things, I have, these have charge. So for your basic leptons, these are negatively charged. And for these guys, their charges are not plus or minus 1, they're plus 2/3 and minus 1/3. So these guys have a charge of plus 2/3 and minus 1/3, which is why I don't put a little plus or minus here. They also have spin. The fermions, they all have a spin of plus 1/2 or minus 1/2. Now, there's also antimatter. So right now I have this number of particles. I have leptons and quarks. I have 3 generations of each. So this is generation 1, generation 2, generation 3. And then for the quarks, generation 1, 2, and 3. And then I have the flavors. So when I talk about up, down, charm, strange, top, bottom, those are the 6 flavors of quarks. We don't usually use the word flavor for leptons. We just call them types, but you have the electron, muon, tau, and then the 3 different kinds of neutrinos. So there's a mirror image symmetry. Mirror is probably not the right word. But they're the same number. They're kind of, the structure is kind of the same way between these 2 different families of things. And that's something that, for no particular reason, no mathematical reason, is something we really like. It has driven the field a lot. Whenever we discover something, there's an imbalance between these, we say there must be another one over here, because we want to keep these two sets the same.
Are these the primary particles?
Yes.
All there is?
This is,
By primary, I mean that it cannot be subdivided anymore.
right. So that's exactly right. These are the primary particles, the fundamental particles, the basic particles. This is the bottom level building block of what things are made out of. I can't take one of these things and chop them to pieces. There might be people, there's certainly people out there who use their imagination and think, well, what if we do this or that? There's also the string theory folks are people that try to figure out what these things are in terms of something that's not pieces of particles, but maybe instead of subdividing these into particles, maybe they're represented by wiggling strings or something else. But in terms of the standard model, in terms of basic particle physics, these are the fundamental particles, the fundamental building blocks. Everything is made up out of this. This is all you get. This and the antiparticles. Each and every one of these guys has its antiparticle, which is exactly the same except opposite in every respect. So for an electron, the antiparticle for that is a positron, which is Na plus. It's just like an electron in every way, except the spin is opposite, the charge is opposite, everything is exactly opposite what it would have been if it were an electron. It's a partner. And every particle there is has an antimatter particle. Now there's some, like the photon, that has no charge. Its antimatter particle happens to be itself. There's no difference between them. Because everything that you would change, if you make it opposite, everything is zero. So you make it opposite, it's all still zero. The only thing that doesn't flip is the mass. The mass is still positive, the mass is the mass. You don't have a negative mass in this case, in this picture. But for each of these things, you have an antiparticle partner for it. In a few cases, like the electron, you write it as E plus instead of E minus, just by convention. The normal way to do it is you put a bar across the top. So for the up, I have an anti-up like that. Anytime I have a quark, I can have an anti-quark, which I'll write like that. And everything, it doesn't matter what force we're talking about, whatever it is, there's always an antiparticle partner for whatever the particle is. I should say that there's nothing a priori special about why particles versus antiparticles. The antiparticles aren't evil twins, they're just twins in some way. It's arbitrary which one we call the particle, which one we call the antiparticle. Nothing makes any difference there. There's nothing like they're the bad ones or the lesser ones in any way. Okay, so that's what I have. That's what the whole universe is made of. Just these things.
John, just one real quick. This is my first time I'm here, and if there are any other people who are here for the first time, perhaps they may be wondering, are any of these, can we see them? Are they so minute that they're not visible to the human eye?
They can't be, okay. They can't be seen by light. They can be seen experimentally. And the important part of the story of how we know these things are here actually is how we see them and are they in fact real. There was a tremendous discomfort with having quarks be anything other than a bookkeeping device because it was hard to accept the way that the picture really is there. We'll see that come up in a while. Yep.
Do the particle forces apply to the antimatter?
Yeah. Antimatter is the same as matter.
No, but I'm saying they have the same application. They work on it. They interface or
Yes.
coupled with it.
Right. The antiparticles are just particles. The only thing that happens is when I have a particle and an antiparticle come together, because everything is exactly opposite, they cancel out, they can annihilate one another, and then it has to turn into something else.
No. What I'm asking is, are these force particles applicable to?
Oh, to antiparticles. Yeah, yes. Everything has an antiparticle. In a lot of cases, it's itself, but like with the photon. But that does apply to the other particles as well. Okay, so here are my forces. First one is E&M, which is what we call electromagnetism. That's the charge force. This is what we're used to all the time. This is the plus charges and minus charges. Okay, the plus and minus come together, plus and plus, minus minus repel. Okay.
With the gluon, if the anti-gluon, would it cause things to fly apart versus holding them together?
No, they work the same way, they feel the same forces. The only thing that is special is when the two of them, a particle and its own antiparticle, come together.
Okay.
They have to be created in pairs in a lot of cases, and they then destroy each other.
Okay,
Um,
okay.
So for the E&M force, electromagnetic force, that's what we think of all the time. We got a positive charge, a negative charge, a plus and a minus. They attract each other. If it's two of the same, they repel. We've been telling that story for a while. Then we have what we talked about, without getting into detail, is the strong force. The strong force, remember, is what holds the nucleus together. That we had the strong force fighting the electromagnetic force. So I had, in the nuclear physics picture, in the nucleus, I have two protons. They're both positively charged. The E&M force wants to push them apart. And the way nucleus stays together is by having the strong force, which overrides that and keeps it together. And the whole story of nuclear fission is the balance between these two forces. But we didn't really talk about what the strong force is. We said there's glue. The strong force, instead of having one kind of charge that's positive and negative, you have something called color charge. Okay. Now color, I gotta say from the beginning, we're not talking about color. It's not light, there's nothing to do with that. The reason we talk about color is because there's mathematics underneath this that none of us want to get into. That it turns out you can represent by colors and it works. I'll show you what I mean. I have three colors. I have red, I have green, and I have blue. Because I have this story of antiparticles, I also have anti-red, anti-green, and anti-blue. And that's just another property these things have. So they have charge, they can be positive, they can be negative, they can be neutral, and they have color. They can be red, they can be green, they can be blue, for the cases of these particles here. Now, the rule is, with color, that I can't have color by itself. I can't have naked color or bare color. You can't ever have something by itself that's going to be red or going to be green. It has to be colorless. There's two ways I can make something colorless. I can take red, green, and blue and put them all together, because red, green, and blue make white. Again, this is a bookkeeping device. This is not what actually happens. So I can have a red, a green, and a blue, and if I have those three things together, that's colorless, and I'm allowed to have that now. That can be a particle in the world. Or I can have a red and an anti-red. And that would be colorless, because I have red, anti-red, the colors cancel. These are not particles right now, we're just talking about colors, things that have this charge. So for example, if I have a plus and a minus, and I want to make something with no electric charge, I can put a plus and minus together. Right? Let's say I could put a proton and an electron together, and if I look from a distance, that will look like it has no charge, even though it's made up of particles that have the same charge. I'm not saying this has to be a proton and an electron, but if I had two things of two different charges like that, they kind of cancel out from a distance. That's what I'm talking about here. So these are not, I don't have a red going around. I have something that happens to be red. It may also be charged with electromagnetic charge. So I have red, green, and blue, or I can have red, anti-red, I can have green, anti-green, blue, anti-blue. There's a number of consequences here. It means if I want to make something that has the strong force, I can only make it in groups of 3 or groups of 2. I can't have one by itself. I can't have a group of any other number. So whatever I have, whatever physical objects I have in the world that feel the strong force have to be made of these kinds of pieces. A red, anti-red, or 2 things, or 3 things. Now, we can start, the third force that's relevant is the weak force, which I'm going to put off talking about for a little while, but we do at this point need to know that it's there. So this is the electromagnetic force, the strong nuclear force, and the weak nuclear force. These are my 3 forces. There are 4 forces, the 4th is gravity. Gravity is, on this scale, incredibly weak and has no relevance at all, and doesn't actually fit into this in any clean way that we know of. We assume that there must be some kind of a gravity particle down here that makes this all work. The charge for gravity would be mass. So the electric charge, color charge for the strong force, we'll worry about a week later, and then mass for gravity. But because gravity is so weak, it doesn't have any effect on anything that we ever do in particle physics. The only place that it comes in at all is when we were talking about nuclear fusion in stars before. That's just a way to get pressure. So these are my 3 forces that are relevant. And now I can come back to my particles and see what happens. In the leptons, these guys are charged. They feel the E&M force. The neutrinos are neutral, they're not charged, so they do not feel the E&M force. They don't feel electromagnetic